I just wanted to remind you that we have a midterm in class on Thursday, in case you had forgotten or were somehow oblivious. So that'll be here. Also, thanks to Bailey, who pointed out there was an error in the solution to this problem, which I think is posted. So this is the one that gives the equivalent semantics for a hierarchical state machine, where you've got these two states, A and B, and it's got this reset transition from B to A and a history transition from A to B. And the equivalent state machine that's shown in the solutions is like this, but this arrow should go from B to E to C to F rather than from C to F to B to E. Otherwise, you would get stuck in this state. So if you notice, I mean, this machine actually has a pretty simple behavior, right? Given an input A, it'll produce an output B no matter where you are, and it just transitions among these states, but the states don't actually change the behavior in any way. So a much simpler state machine that has the same input-output behavior is one with a single state and a single self loop that, just given an input A, produces an output B. Okay, so hopefully that posted solution didn't confuse anybody. You probably all saw right through it. Okay, so we're going to start with the project, with the projects, more or less. Given no other basis to pick an order, we'll pick an order, the order that is here on the spreadsheet. Okay, so what I'd like to ask you to do is each team should come up. If you do have something to show, you can plug in. If you don't have something to show, that's fine. You're absolutely not required to have anything to show, and not even encouraged at this point. But it's okay if you do have something to show. In either case, I ask you to, when you're speaking, to use this microphone, because it'll get recorded. And I think it'll be interesting, at least to you, to go back at the end of the semester and take a look at what you thought you said you were going to do, or what you said you thought you were going to do, and compare that to what you actually did. Okay, so of course, if you really don't want to record it, just leave the microphone on the table. That's okay too, but I encourage you to use the microphone and record it. So, all right, so is Sarah, Danica, Umberto, and Alex's team here? I see at least some of them, so why don't you come on up. And I'm going to disconnect this to not be distracting, and also so that I can take notes on the side. All right, so here's the microphone.
Hi, we're the players. And the reason we're named that is because we're doing the project with DDR. It's going to be a DDR player. So what that means is it's going to, DDR, the free one online, is going to be streaming on the screen. And then we're going to have something that somehow captures the information we want so that our player can do the right steps and dance the night away. So anyone else? Okay. Oh, any questions?
Do you have an idea of what hardware you're going to use, or what platform?
I already spoke. So.
Well, yeah, Danceport will probably be useful for DDR. I'm assuming probably like a webcam to capture the streaming video. And probably, I'm assuming like we're using some open source software to hopefully translate the images into something useful we can use.
Are you going to use Kinect to do something with those images?
No.
Probably no.
What are you going to use for a dance floor?
I'm not sure yet.
Yeah, we're not sure yet on that part.
And your mentor is?
Kevin.
Yeah. All right. Good. Thanks. All right. Okay, the next team is the most significant bit. Bailey, Ibrahim, Ted,
We lose Ted. So we're going to be doing the robot train project. We're going to be using the iRobots. I think we're going to outfit them with some sensors on top, an circular array of infrared LED emitters and sensors to try and get some, each one can tell where the others are, and then they can communicate this to try and get into a line from any configuration and then follow each other using the LEDs. Hi. Oh, questions? Friends? How many iRobots do you need? I don't know. I mean, ideally we could do it with any number, but at least 3 to make it any interesting. Yeah. Are you using the localization stuff? Cameras that are set up? No, we wouldn't be using the cameras in the lab. How would it work exactly? I mean, with the array of LEDs, they have a few examples of these in the 3rd floor windows, but you could tell what directions the other ones are in, and then each one would have an idea of where the others are. So I don't know if we could get distance between them unless we moved around, see how it changed, but we could tell orientation to each, and so they would be able to we go towards each other and get into a line. Yeah.
There was a project, I think, 2 years ago that might be a useful reference point that used lasers on top of the robots and used the robots to, to swing the laser around and they detected it and they were relative to one another.
Okay.
That might be a useful thing to take a look at.
Cool. Do you know who did that?
I remember that Jeff Jensen was on that team, and he's still in contact, so we can put you in touch with him.
Cool. Thank you.
But you have the previous message videos online, probably?
Yeah, the video would be online, so that would be a good place to start. I think it was called robot localization.
Okay.
All right. Did Ted show up while they were? So Ted's still missing. Okay. All right. Team 3 is I Squared Guitar, which is Dorian, Tom, and Gautam. Is that how you pronounce it? Gautam?
It's actually 2 other people as well.
Sorry?
There's actually 2 more people, but
Oh, okay. Who are the 2 more people? Niloy? Niloy and Cameron. Yep. All right. So you have a 5-person team.
Okay, so we're doing our project on what should ideally be sort of a retractable electric guitar. So a belt clip, and you can attach, well, we'd be doing it with a microcontroller initially, but at the end, we'd hope to be able to attach an iPhone into it or an iPod or whatever and pull it, and it'd have an interface, and there'd be retractable strings, and you could strum the strings to simulate plucking, and then it would detect the vibrations, and it wouldn't actually be using the strings as the noise generation. It would be using like MIDI files or something to imitate actual guitar strings. And then, yeah, and then on the handle, you'd have an interface that simulates frets, and you can pull different amounts to be able to determine the pitch. Questions?
What platform do you expect to use?
Haven't quite figured it out. We're initially planning on trying to just do it through a microcontroller of like something simple, but we haven't figured out exactly what we have access to in terms of equipment, so undecided as of now. Questions?
And who's your mentor?
Thus far, I don't know if we have one because it's not actually one of the listed projects. So. Yeah, so we'd like to see what equipment are actually available that we can take advantage of. Okay. Okay, yeah.
Okay, good. So where are your two other team members?
No idea, they're not here right now.
Okay.
Figures, right?
They didn't fill in and didn't show up. Okay. All right. So next is the TBD, which is Raphael, Gayan, Kartik, Apurva, and Jacob. I think they just hadn't decided yet.
Hello, we're TBD, and we named it such because at the time we didn't think of a name, so we just said to be determined. And we plan on using the Husky, and we would like to use it to navigate around Cori. So that actually includes use of the elevators and possibly even having a map of certain rooms where you can say, go to this room, and it'll get there. So we've divided the tasks up a little bit, and we're just going to give you a brief summary of what each person is doing. So want to start at that end or come this way?
Hi, my name's Karthik. I'm going to be working with motion planning and basically the software side, getting the Husky to go where we want it to go.
Hi, my name is Apurva. I'll be working, helping out with the motion planning and then basically doing the elevator planning and how it's going to detect the buttons and use the camera.
Hi, my name is Gaine, and I'm in terms of communication and making sure that we can get data from the robot as it goes around the whole building.
My name is Jacob. I'm going to be doing low-level sensor and actuator interfacing, so writing low-level APIs for the software people to use and calibrating the sensors.
Hi, I'm Raphael, and I'm going to be in charge of getting the hardware running. So we're going to need an arm so that we can press buttons on the elevator and a camera. So for the arm, we're probably looking at using the servos and the hardware that's already in the lab. But for the camera, we are wanting to use a CMU Cam 203, so I don't know if that's available, and so that's something we'd be interested in using. And for localization, either infrared or ultrasonic sensors, depending on what's around. So, any questions? Okay, so we're not actually sure because we haven't seen it yet. So we were told that it's very similar to the SP Rio, and it should be easy to get used to the other one if we know how to use the SP Rio. So. Oh yeah, we're thinking of sticking with the state chart implementation because that seemed to be pretty flexible. Yes. The way you use that is it spits out serial, so you can configure it to do blob tracking and of different colors and coordinates, so you can just use a serial stream. Yes. And
your mentor is?
Oh, Winthrop. Is he here? Yeah, he's here.
All right. Well, that's so far the best organized project. I like the assignment of responsibilities. Those can change over time, right? But it really helps get things going if you assign responsibilities to your team members. Right?
Yeah. If we take it outside, maybe. Okay.
Okay. The next project is called SLOP. Samit, Luke, Oren, Alash.
Wait, we have to be in the order of slot.
No, I don't think we do.
Okay.
The name is your
All right.
So introduce yourselves when you start.
All right, yeah, so I'm Luke.
I'm Oren.
I'm Palash.
I'm Sameep. And we are Team Slop. And so our project is to make a musical mime bot. And so the idea of it is that you'll like have this bot next to some piano or some other instrument, and then you play a really simple tune like Twinkle Twinkle Little Star, or like if we get really good, maybe something fancier like For Elise, I don't know. And then it'll figure out what the musical notes are, and then it'll also try to figure out what the beat is. And then it'll be mounted on either some kind of like piano, or we were thinking like a circular xylophone, and it'll like zoom around the xylophone and just kind of like hit the notes in time so that it like replicates the song. Any questions? Okay, yeah. Oh yeah, okay. So for who's going to be doing what? I'm going to be doing stuff. Oren's going to be doing stuff.
No,
Come on. Okay.
No, I mean, so there's on the software side, there's motion planning. Like you need to do like shortest path. So if you play like a C and then an E, you just want to go right a couple of notes rather than going the long way around. For example, if it's a circle. There's also a lot of like signal processing to be done on the audio source. Luke's pretty good at signal processing and things like that. Also, Palash and Luke are pretty good at the hardware side, so we'll be able to look at getting some, my robotic arm stuff going for that. Do you guys want to elaborate on the computing side, like the Atom stuff?
Well, yeah. Well, for one thing, our design is really nice because it's very layered. Like we can first start out like instead of trying to interpret like piano, we can just start interpreting like just sine waves and just getting that like correct. Like say this is just like a C, like an A440 or something like that. Hertz sine wave, and then go beyond that and add more like harmonics or have more complicated machinery. And then also for the actual like hitting the notes correctly, we can start out just having it like sending it MIDI messages, which is just a serial protocol, and then making sure that it gets the timing right, and just build across that. Anybody want to say anything?
Sure. I think for the hardware design, what we want to use is an Atom board because that will really simplify the signal processing, taking like Fourier transforms. But we're also pretty open to other considerations. Any questions?
I mean, if you're going to be running around a xylophone, the notes are going to be physically different distances apart, even though you might be. What are you going to be using that can change speed that fast?
So we have a couple ideas. One idea is we mount infrared sensors on the notes themselves, and then we can know where to start and stop. So that would kind of help simplify that problem.
And another advantage to using a circular design is that instead of having to like hit one note, then go back again, we can just go around and just like increase the speed each time, so it never really has to like stop completely. Okay. All right.
I have a couple suggestions and comments. I just want to borrow the microphone. First of all, interesting project. I should point you to a challenge problem that was posed by a European Union-funded project called Artemis. And Artemis was launched, I think, around 2006, and it's actually still going, and it's a huge research project in Europe that has, I don't know, something on the order of €1 billion per year getting invested in various ways. But as part of launching it, they issued a challenge problem that they called the Artemis Orchestra. And the challenge was to make a machine that would play a musical instrument as well as a human, an unaltered musical instrument. Okay, so the idea was that it had to, play a flute or play a horn or play a piano. And I went to one of their kickoff projects, and they had a demonstrator, which was a piano that they had equipped with a device that hung over the keyboard that just had a bunch of solenoids, one for each key, and they were computer controlling it to play something. And they had it playing Schoenberg because I think that was the only composer they could identify where no one would really be able to tell whether the pianist was playing well or not. Well, Schoenberg, he's an avant-garde guy who does the 12-tone thing. You're not allowed to repeat a note until you've played all 12, right? Yeah, so it's right. It's slightly bizarre stuff, but anyway, challenging problem. But I do have a couple of suggestions. One is that for playing a xylophone, you might consider maybe we can find an old printer with a movable head, right? Take it apart and attach a solenoid to it. They're very easy to control because they're designed to be controlled by computer. So that might be a very simple way to get an actuator that would, that you just have to adapt rather than build up from scratch. And the other suggestion is that note recognition from audio signals is an extremely challenging signal processing problem. I would recommend that you try to find some open source stuff to use rather than spending a lot of time on the signal processing. I think the signal processing is fascinating, but more appropriate for a signal processing class, right? So try to find stuff you can just use instead of trying to reinvent it. Yeah.
I suggest just putting one solenoid over every note you want to hit if there's not that many notes, so you don't have to worry about moving back and forth.
Yeah, that would be.
The moving back and forth is awesome. I want to see that. Okay.
Yeah. Go ahead.
Yeah, well, one thing we were thinking about the keyboard though is that with a xylophone, like you can really quickly just like tap it just with a solenoid, and like you wouldn't need that much force, just velocity. But for a keyboard, you might need to like press down harder, but we can certainly check that out. Well, yeah, you can get a MIDI keyboard that. Yeah, that's true.
I feel Schwartz. East Coast.
A potential suggestion, or potential theoretical, but that you could try in terms of hitting the xylophone. If you're having difficulty when the thing's spinning as you move, what you could do is you use keys. To strike them. That is, you wouldn't need contact. You would just. So that would make the thing ring.
That's very cool. Oh. That's awesome.
Thank you.
Okay.
Sorry.
Sure.
If you use
So you guys also need a mentor, right?
Yeah.
Okay.
We're thinking about when to finish it.
That's a great idea. Yeah, let's connect you up with someone at SynMat.
Okay.
They can really help on the signal processing side.
Oh, awesome.
So, all right. Okay, good. The next team is Charles, Dorsa, Nima, and Farshid. Is that how you pronounce it?
Yes.
Okay. All right. Hi. Okay. We still don't have a name, but we are thinking about configurable robot, maybe. So our project is the high-level command execute robot with Ben Chowley. So our mentor is Ben Chowley. And the way it works that you give it an English sentence, or you can even tell it, and it does voice recognition. It converts the English sentence to LTL, which is linear temporal logic. And then after that, it converts LTL to some Verilog. And then we convert Verilog to C, and then actually, or LabVIEW. And then at the end, it's going to actually execute that. So let's say that we have 2 robots here, and we tell one of them to go to the kitchen, and like we define where kitchen is. And so we have to do some localization here, and we are probably using the localization system to give it the map. And it actually goes to the kitchen, but it has to figure out how to get to the kitchen. So that's also one of the problems. like avoiding obstacles and the things that we did in the lab. Anything you want to add?
Hello, everybody. My name is Nima, and I think like we have like some points that we're gonna get to. So first, we're gonna like just make a connection. So it reads the text, and then we convert it to like instructions for the robot to do them. And probably later on, we might add like the voice recognition, and we might like just make it like dynamic. So if it wants to know where the kitchen is, it dynamically recognizes where the kitchen is. And also, we might add like something to like when we tell it to do something, it says like response to us, says like okay, or says yes. and after it finishes the job, it just like confirms that it's done and it needs to like a new instruction. If there are any questions.
Just a quick thing to add. For hardware, we're going to use some other sensors maybe, but we haven't really looked at it yet. In terms of the platform we want to use, we are thinking about Aspirio, but we're not sure yet because it depends on how much memory we need. So, questions? Okay.
I'm just wondering, like, I know there's a good reason.
Well,
Part of it's done.
part of it is actually done. So, like, going from English to LTL, I think we can find some libraries that can help us. And going from LTL to Verilog, it is not. I think that's also already there. So we have to just convert Verilog to C, and that Verilog is apparently not that bad.
Why is it have to go LTL to Verilog? Because there's already
Yeah, there's already like things that we can use for to instruct to C. I think I'm not sure. I have to look for that, but I think the Verilog is just going to give you the state machine. So we need to actually like to some embedded C. Yeah, we have to convert it. Yeah, that's why we have it in Verilog. Kevin. Yeah. Yeah, so the only thing that we're planning to send is the C code, the embedded C, or LabVIEW.
The Rio? The mechanical platform? You mean like the oh, it's the iRobot. Yeah, the iRobot is going to be moving and probably has like a Rio board on it.
So depending on how much memory we need, we might want to
switch to like a. Yeah.
I think we're fine with iRobot for now. With the Aspirio right now.
Do you have a way of distinguishing between useful commands and just random people talking?
First, we're not going to actually have it like recognize the voice. First, it's going to just read the text and then like translate that text. And then later on, we might add like voice recognition, and then that's going to be a little bit harder.
So you have some hardware on board, but which is not connected to the robot yet. Sensor, but one of them cannot connect, right? And then say, okay, the robot can go ahead and reconfigure the FPGA and get that input in.
Yeah.
More interesting to do this because it's both like platform generate. It generates the hardware.
Yeah. Okay. We look into it.
Yeah, I think we should move on. So, Team 7, it says, is just one person, Rajat? Is that right?
Oh, actually, he moved my team to the last one. So.
He's on which team?
So from group 7 to group 10.
Oh, okay. All right, good. That makes more sense. All right, so let's go to group 8, which is also called TBD. Humphrey, Ryan, Leo, and Eric.
Don't chalk it. You don't want to chalk it.
Be here for the rest of our lives.
So long. But it's a good time. Okay, hello everybody. Oh, it's a little loud. Okay, so I'm Ryan. This is Humphrey, Leo, and Eric. And we're going to be working on, I'm calling it Multi-Agent Collaborative Target Range Finding, which I know is a very simple name. But basically, here's the idea. So you have, let's say you have some target in the room. Let's say it's a big, bright beacon. And you want to find out where that target is. And you have robots with low-fidelity sensors moving around. Let's say they're cameras. So each robot can get a really terrible estimate of where it is, of where that object is, because it can look with its camera and give you a really, really bad range find on it. But if you can combine all of those measurements from all of the robots, you can probably get a really good range find on it. So the idea is to use sensors that are otherwise useless for a single robot, almost useless for a single robot, but in groups are really useful. And so the idea we have is to, again, have a beacon in the middle of the room, have, let's say, 3 to 5 robots moving around. They each take noisy range finds, perhaps with a Wiimote, perhaps with an Axis camera. And you take those range finds, you provide a communications infrastructure for the robots to communicate these measurements to each other, and then each of these robots come up with an estimate of the position of the beacon in the middle of the room. Anyone? Questions? Anyone? So essentially, if we want to get more complicated, so the state estimation for the target will be like this Bayesian algorithm. Oh my God, I used the word Bayesian. Bayesian algorithm. And usually, so path planning we haven't really explored that deeply, but essentially you would want to go to the areas of the room. So the robots imagine the world as a state space, and you would want to tell the robots to go to the areas of the state space that are less explored. So they have an idea of which parts of the state space are explored, and they'll try to go to places that are less explored to make their measurements better. And now I'm going to make Humphrey talk.
So hardware-wise, we're planning on using the SPRIO on iRobot Create. For sensors, we're looking at the Axis Cam, as Ryan's mentioned, and also we've discovered that the Wiimote has a CMOS camera that does hardware tracking of IR blobs at 100 hertz, so who would have thought? And that's just interfaceable through I2C, yes. So the I2C device actually doesn't let you get to any of the frames, I believe. It just returns XY coordinates and strengths of IR blobs. It tracks the 4 strongest blobs, which may be an issue because we're also thinking of using the Vicon, which will be throwing IR all over the place. But we'll see how that works out.
How many robots?
Oh, 3 minimum, maybe 4 or 5. Yeah.
Okay, I mean, so we have tentatively divided the labor. So I believe Humphrey's going to be working mostly on sensing, so that range finding we were talking about, either the Axis Cam or the Wiimote. I'll be working on target state estimation, so that's the sort of 188 material I was talking about. Leo will be working on motion planning and low-level control, and then Eric will be working on communications. Okay, and no more questions? Okay, cool, we're free.
Okay, next is Team Venture, Ashley, Ian, and Chris.
Hello. Okay. So we're doing the floating sensor network. So in the entire I'm Ian, and this is Ashwin. So we're going ahead and using the software, the architecture, with collecting the salinity measurements from the floating sensors, and the key component of this is the communication, not just commanding the programming the microcontroller, but also the communication between, let's say, a Linux computer sending commands to collect data or maneuvering around the individual pieces. And so we were thinking it already is installed with a Google protocol buffer, so we were going to use that for part of sending information back and forth over the network and collecting GPS information, and then using the microcontroller and actuators and sensors already on there to try and collect the salinity measurements. Any questions?
So is the goal just to record the
Well, there's also there's other commands I believe that we haven't really looked, but like basically because the Unix or the Linux should be able to like send various commands about like movement and other processes that they would want the controller to be able to do. Yes. We haven't really figured that out yet. We were going to look into it.
And some people, just a suggestion, some people have made all the electronics up in the top part, and then the bottom part where you hook up the pipes.
Yeah. Mm. Yeah. Yeah, yeah, because we are working with.
Okay. So one thing that I would suggest is that there.
Mm.
Right, but there needs to be some actuation.
Yeah.
So maybe the robots.
Well, because they have to move up and around the water to collect them, and they're not just staying in one spot. So part of like figuring that out and getting around objects in that environment.
Okay. Good. All right.
Perhaps I guess. I think.
Well, I think
But you do have that first mining fountain.
Fun.
We actually have a 5x5 thing. But we also
All right. Good. Okay. The last but not least is High Templars. Min, Huang, Daniel, and Rajat. One of you is missing?
Hello, my name is Daniel, and our team doing the StarCraft project. So basically, we have a environment which is enclosed space, and we use the optical tracker to identify where the robot is, and we have a virtual commander to send requests to the robots and let them to find the shortest way to the destination.
So the objective of our project is to interface the physical structure with the robots, 3 to 5 robots, and the system will send a list of commands to the robot to tell each robot to go to a given list of destination, and the objective is to try to minimize the time to finish each request, and then yeah, that's pretty much all.
Okay, so my name is Huang. First, that is the basic that we learn how to when we finish on the basic of the project. So what is in our head that we will make this more interesting by like the map will not be visible to all the iRobot. So we will make them go through all the room, not all the room, but some part of the room to share for the map. So then the map will be visible to all the iRobot. And because we all prefer the AI, we are on sales major. Like we don't like the sensor. We like something more machine learning. And so we just think about that. We first make on the iRobot go around the room and search for the short path to the mining. And who first encounter the mine will signal to all the robot, hey, there's a mine over there, and just go there and get it. And so just and one more thing is that we can. I mean, there's a lot of things that we can do with 3 robots and the map. Like we can make them do cat and mouse, like one high and another will seek. Or we can make one commander like every before they return to the mine to the source, they need to go through the commander and hey, I got mine, and then I'm coming back. There's a lot of stuff we can develop from the basics. So that's what in our head now. Thank you. Any question? Yes.
Wait, I have a question. Yeah. So you're going to use the optical tracking system that Dorset has set up, right? And currently, I think that generates a Bluetooth signal. Back up to generate a network signal. Is that what you're going to use? I think we use Wi-Fi. Okay.
And your mentor is Dot?
Yes.
Okay, I'd like to just encourage everybody to set some short-term goals, things that you would like to have working in 2 weeks, okay? And figure out who on your team is going to do which part of them and get started, right? So that after spring break, you've reached a milestone, you've got something, right? And some of these projects are very ambitious, and we'll have to scale back. But you should set something very modest as a short-term goal and get something accomplished. Yeah, Trung.
I have a question. Like, in general, team going to get the
Yeah. Well, I think that for all except the water tanks, the work should be done primarily in the lab. Okay. Yeah.
I'm also hoping that Ryan can move the screen to 125 forward because he already has access.
Okay. Well, we can get access to anybody who needs it to 125. Yeah. So I mean, if you need more space than what you can reasonably get in the lab, let us know and we'll work something out. Yeah, Dorset. Right. So if there are 3 groups that are going to be using the optical tracking system, I think we're going to need those 3 groups to coordinate, right? So you should appoint one person in each of those 3 groups who is responsible for the optical tracking system, and then those 3 people should coordinate amongst themselves, okay? Ideally, I mean, in the ideal world, the optical tracking system would work in the background like GPS, right? So it can be set up to just be broadcasting Bluetooth, or maybe, you know, if we convert it to Wi-Fi, it's just, you know, sending out information on Wi-Fi, and there's no reason why two groups couldn't use it at the same time if that's happening, right? Aha. So when you say one shared code, what do you mean exactly?
I mean, one shared code getting the data of all the robots that have.
Right.
And then it gives broadcast.
Right.
It's like a server, like server-based and query kind of thing, or is
Yeah, I don't know, but this is going to have to be part of the project effort, right, to figure this out. So.
I might suggest that the 3 people from each of those. Probably not going to use the space simultaneously because the viewing space of the optical system is fairly limited. But you want to be able to jump in with your robots as soon as someone else goes out and not have to restart it.
Yeah, but you know, the fact is the vast majority of the time is going to be spent on things that are not directly using the localization infrastructure. So I don't think it'll be a problem to time multiplex it, right? But it will require coordination. And in particular, one of the things is you want to be able to make sure that one team doesn't mess up another team's setup. So there needs to be cooperation, right? Yeah. Right. Okay. Yeah, if we need more, we can buy more. Okay. Yeah. Yes. We should put the Husky in the lab. Where is it now? Let's put it in 119. Well, I mean, it's only this big. There's room. Yeah, we can take the ramp out. Okay, I guess that's it for the projects at this point. So I encourage you to, use the lab times, at least initially, as your primary time for your team to get together in the lab, and the Kevin and Dai will be there during those times as usual, and can help you out with the coordination. Okay, and if you do need to purchase hardware, you should that should be your top priority is figuring out exactly what you need, because sometimes there's a lead time. Well, there's inevitably a lead time, sometimes several weeks to get stuff. So, yeah.
Do you want to encourage CalDay participation?
Yeah, that's a good point. So on April 16th, how many of you have been to CalDay? Okay, so you probably know it's kind of fun, and it's I think it's really kind of popular in the local community. A lot of people come to see what's going on, and traditionally we do demos from this class, right? So I would strongly encourage your team to do this. I think that one of the key incentives is that it's a relatively near-term milestone where you'll want to have something to show, and it need not be complete. But it just, for example, just being able to show that you can control the Husky robot, for example, and have it do simple things and show off the robot at CalDay, right? Or show off the localization infrastructure, what it does, right? That you know, you have to get to the point where you understand what it does and how to use it, right? So it's a relatively near-term milestone. And so if you want to sign up to do that, Dai is going to be coordinating our CalDay presence. We will not be opening up 119 Cori, so we'll have to move the setup to somewhere else because we don't want a bunch of random kids with sticky fingers wandering through our lab. So, you know, the setup will have to go somewhere else. But that's actually also good practice because the project demos at the end will be somewhere else too. Normally we do them up on the 5th floor in the DOP center. Okay. Any questions? Comments? Yeah, Raphael.
Would there be a certain time slot where I'll
On CalDay? The question is what time? I think there's a. Right, and so we could. So my recommendation would be to choose one of those two slots, 10 to 12 or 1 to 3. Don't do both. It's just too much. You end up exhausted by the end. Okay, and I think we can accommodate whichever time slot you prefer. So shouldn't be a problem. All right. Yeah, question. Yes, the date and time for the final project presentations is finalized. It's on the website. May 10th, 12:30 to 4. What? If you have an irreconcilable conflict with this, I would like to know soon. But this is the scheduled time. And I think it is important, to have them all together. One of the things we do is we videotape them, which I think is pretty useful for people who take the class later. And it's also kind of inspirational for other people out there to kind of see what can be done. Yeah.
Exact that date from 11:30
Yeah, we can work around that. So we'll schedule you. So you're going to be like, you'll have a final from 11 to 2?
Yeah, 11:30 to.
Yeah, so we'll schedule you towards the end of the time session. That's.
Oh, actually, that will work because I have another final, so I have two finals that day. 11:30 to whatever, and then she to. I have 141 and 120 back to back that day.
Okay, well, you better drink lots of coffee that morning. Yeah. Yeah. Yeah, it's true actually. I mean, I know of at least 2 or 3 instances where companies have gone and actively recruited people based on the project presentations. I know that both Intel and National Instruments have actually hired people based on these, or at least it kind of got started that way. So it does happen. Okay. So what's on the schedule is to do a midterm review. I could do a midterm review, or I could talk some more about scheduling. Shall we take a vote? How many would like to do a midterm review? How many would like to talk about scheduling? Okay. That settles that. Okay. All right. So the focus of the midterm, as you know, is basically the material up to, but largely not including Chapter 10. We started in on Chapter 10 and 11, which was multi-threading and multitasking. But I do want to emphasize that one of the key concepts in this midterm is the basic idea of dealing with concurrency in software. And so a basic notion of what threads are and what interrupts are is essential to the midterm, okay? So just going through the topics that we've covered so far, the key thing to keep in mind is that the focus of this course is less on the optimization problem of embedded systems, so not so much on, dealing with the idiosyncrasies of microcontrollers and that kind of thing. That's kind of an essential part to getting stuff done, but the real focus of the course is on the interaction of something that does computation with something that is a physical process. And that dialogue is really the essence of what we're interested in. Okay, that's why in the projects, for example, on this, we're not a project that is purely gathering of information from the environment isn't going to have this nature. It doesn't have this interaction. It's just information gathering, right? Okay, so the other thing to emphasize is that even though the subject of this course is really quite immature, the goal of the course is to give it as much of a principled approach as is possible given the state of the technology today. And I freely admit to everyone that that's a limited amount that it's possible because it is a fairly immature subject. And so to some degree, there is still quite a lot of kind of seat-of-the-pants ad hoc things that get done. But to really shine in this course, you need to sort of step back and identify the principles. So, in particular with your projects, you should think right from the beginning, what are the principles that apply in your project, okay? And that's being able to make a good story at the end about how the reliability or the unreliability of the system you build can be analyzed using reachability analysis of state machines, for example, or something like that. That kind of a story about how that connection between what you build and the principles, that's really a major part of the focus, okay? And what we're trying to do is sort of steer people away from just hacking, and that's not to say that we want to steer you away from doing experimenting. You should do experimentation. But the goal of experimentation should be to refine your models. Okay, so you find out where the weaknesses are in what you thought was going to happen, and then you refine your models and you improve your system. Okay, so a big part of this is modeling. So this interplay of modeling, design, and analysis is the focus, right? And I think I went through definitions of these terms, but I'll go through that rather quickly. So we started, as you remember, with the notion of modeling continuous dynamics. And there, the key concepts that we introduced were really twofold. One was using ordinary differential equations to model continuous dynamics. So dynamics is the evolution of the state of a system in time. And you'll see that a lot of the modeling that we've done has been focused on dynamics of one sort or another. And ordinary differential equations or integral equations are all about representing the change of the state of a system over time. The problem with doing modeling using purely differential equations is that it doesn't scale very well. Okay, what happens is that if you try to design complex interactions or understand complex interactions between heterogeneous components, you might be able to analyze each individual component using some approximation using ordinary differential equations, but when you try to put that component together with something else, if you try to come up with some overarching homogeneous model that is described using ordinary differential equations, things break down. So a very simple example of that we talked about early on is, an accelerometer you can model as a spring mass system, okay, where you make a measurement of a gap, okay, and as you rotate that, the gap separates because of the effect of gravity, and you make a measurement of that gap, and you can certainly model the dynamics of that sensor using a differential equation. But if you want to understand how that sensor interacts with your robot control algorithm, it's going to be hard to just construct a bigger differential equation that describes that interaction, right? So I gave you an example. I mentioned that when I first implemented this hill climbing lab project, that my first version caused the robot to start dancing on the platform when I put it on this inclined plane, which I made out of the center leaf of my expandable dining room table, okay? And the reason it was dancing was that it was measuring its own motion and using the accelerometer, and then that its own measurement of motion was confusing it about the tilt that it was seeing, and it was reacting to that by and overreacting to that, okay? And so, I could have tried to construct, a joint differential equation model of the accelerometer and the robot dynamics and the motor dynamics, but it would have become very, very difficult rather quickly, okay? And so the idea that we introduced, the key idea that we introduced, was to combine these differential equation models with actor models. And so you have an actor is simply a component that has inputs and outputs. The inputs and outputs are kind of idealized as continuous time waveforms, was the ones we started with. And then you compose these things as if the only interaction between them is those continuous time waveforms. It's an approximation, right? The interactions are more complex, but it's a useful approximation. It gives you a way of breaking down a system into pieces, okay? And of course, this notion of breaking them down into pieces in this way, of course, fed into the lab content, I think, fairly cleanly, because LabVIEW is really based on this principle of building up systems in very much this way, okay? We then fairly quickly switched to discrete models, and a few of the key ideas in discrete models is that if you have a component that is discrete, what we mean by discrete is that it changes state in abrupt, singular steps, as opposed to changing state continuously. And in order to have this notion of it changing state in abrupt steps, you have to somehow define when those steps are going to occur, okay? And a big part of the choice in modeling is actually trying to figure that out. When do the changes in state happen? So we had the notion of a reaction, and a component reacts at some point defined by its environment. When it reacts, it observes its inputs and changes state as a single atomic action, okay? And we talked a bit about various ways of structuring this notion of reaction. The one that I think we used the most was where the inputs to a discrete component and the outputs were continuous time signals, in the sense that they're defined at all times on a real line. But they could be absent, and in fact are absent for most of the time. The only time they're not absent is when reactions are occurring, okay? We then talked about hybrid system models, which, we have the FSM notation, which I think you're all familiar with now. We then talked about hybrid system models in which a component can blend this notion of a discrete reaction with a notion of a continuous evolution. So the key idea in hybrid systems is to be able to have those two things coexist. So a system can be continuously reacting to inputs, evolving its state continuously, but also at specific discrete points in time, make abrupt transitions. Okay, that's the key idea in hybrid systems. And most of the hybrid systems that we worked with were of a simple form that are known as timed automata, where the evolution of the state of the system was a simple linear function. Okay, and I think if you just focus on hybrid systems that have that timed automata structure, that'll be sufficient. You don't have to worry about more complicated dynamics because they can get very complex, hybrid systems. It's a very interesting subject. There's a graduate class that we teach that focuses on analyzing hybrid systems from a control systems perspective, and it's kind of beyond the scope of this course. But if you understand timed automata and this mixture of this linear evolution of state, which is really just measuring the passage of time continuously, and then discrete transitions, that should be sufficient for the midterm. Okay, so this is an example of a timed automata that's describing a traffic light system, and what makes it a timed automaton is that the continuous variable, in this case x, is its dynamics is defined by a very simple differential equation where the derivative of x is just a constant in all states of the system. Okay, I want to emphasize that also you should clearly understand what the notion of state is in a system. So how many possible states can this system be in? Sorry? 61 times 4. Where does the 61 come from? Yeah. X is not discrete, right? X is a real number. I think you're remembering a different variant, which was a purely discrete variant that used extended state machines. And that one was a finite state system. This one is not a finite state system. And just the fact that it's represented with 4 bubbles doesn't make it a finite state system. The number of possible states of this system is infinite. In fact, it's uncountably infinite because at any given time, the value of x can take on any real number. All right. If you look at the dynamics of this, it can actually take on any real number, right? Maybe greater than 0. Is it true? Can x ever be negative? Yeah, so these would be, by the way, really good quick answer questions on the midterm. Okay? Is x equals -1 a reachable state of this system? Is x equals 61 a reachable state of this system? Okay? And you should be able to read these diagrams so that you can tell me whether whether those states are reachable. Okay? So shall we take this as a measure of how well prepared you are? How many people think x equals 61 is a reachable state? Okay, those are all timid hand raisings, but how many think it's not a reachable state? Also timid hand raisings. I would say most of you are not ready for the midterm. Yeah. X equals 61 is reachable, right? If you're in the green state, the dynamics of x is it's going to continue increasing until what happens? Well, one of these guards has to become true. Okay? And that's not going to occur if no pedestrian arrives. All right? So x is going to keep increasing until a pedestrian arrives. So x equals 61 is definitely a reachable state. -1 is not a reachable state, right? Because x is only increasing and it gets initialized to 0 and it gets reset to 0 on 4 of these transitions. Okay? Yeah. Sorry. Yeah, I mean, you could create a variant of this that had another transition out of the green state that was enabled in the absence of pedestrian. But you have to be a little careful, right? Because pedestrian is a pure input. So how often is it absent? Most of the time, right? So if you had a transition out of here that was simply enabled by pedestrian being absent, how long would you spend in the green state? If I had a transition out from here that was enabled by just the absence of pedestrian. Yeah. Yeah. That's true. So there's always an implicit self loop, right? If none of your outgoing transitions are enabled, okay, there's an implicit stuttering reaction where you just stay in the same state, okay? So that's here. So if pedestrian is absent, we just stay in green and keep doing this dynamics. Okay, but suppose that I had another transition out to some fifth state over here that was enabled if pedestrian was absent. Okay, this would be another good short answer question on the midterm. Okay, I would draw a variant of this, have a transition to a fifth state, enabled by the absence of pedestrian. And the question is very simple. How long does the system spend in the green state? 0 time. Exactly 0. Right? That's right. If I had a pedestrian out here, transition out of the green state that was enabled by x being greater than or equal to 60, then 61 would not be a reachable state. That's correct. Okay? Yeah.
So for the previous example, when you had the extra guard,
yeah.
What happened when there was no pedestrian? Would the time in green be 0?
Well, so actually, let's think about this a second, because so the scenario is I've got a transition out of here enabled by pedestrian being absent. Is it possible for pedestrian to be present for a continuous region of time? If it is, then I could actually spend non-zero time in green. Okay? If the pedestrian signal could be, let's plot it versus time, it's either present or absent. Okay? And here's time. Here's a real number. If it could be, so normally we think of it as a discrete event. So it occurs instantaneously, it becomes present, and almost everywhere it's absent. Okay? But suppose that instead we allow it to be present for some period of time like that. Then, in fact, I might end up spending non-zero time in green. Okay? What's the difference between a signal where I allow this versus a signal where I don't? Yeah.
One more question. Is it still within the definition of a pure signal if you do that?
You know, I don't remember exactly how the book defines a pure signal. It may be. Okay? The issue is that this signal is not a discrete signal. Okay? There's a rigorous definition in the text of what a discrete signal is, and this is not discrete. Okay? And the intuition of a discrete signal is that if you look at all of the times that it is present, okay, that you can list those in order. As a list. Okay? And only if you can do that is it a discrete signal. In this case, you cannot list the times that this is present in order. Okay? Is it clear, that distinction? Yeah.
So that's because you have an infinite number of possible ones in that construct.
Yeah.
So if you put the discrete one in front of the...
Yeah, good question. So
Would that be non-discrete? Because you theoretically can list them on just with infinite list, but
Well, you can't list them, right? Because, suppose this is at time 1.0. What's the next one after it? What? Yeah, but this is reals. So you still can't list them, even in that case. But excellent question, right? Suppose that this is present at all the rationals and absent at all the irrationals. Then is it discrete? Still not discrete, right? What's the next rational after 1.0? Well, there isn't one, right? Yeah, do you have a question? Sorry? You mean with this variant, or? Oh, if we allow this? So the scenario is if we have a transition out of green that is enabled by not pedestrian, okay? If we enter the green state at this point in time, then there's a bunch of time after where not pedestrian is false, so that transition is not enabled. Not if time is less than 60. Sorry? Oh, you're right. It would go to pending. You're right. It would go to pending. You're right. It would still take 0 time. I wouldn't have done very well on that midterm question. Yeah. Right. So that's the assumption we make with hybrid systems, is that they're continually reacting. Okay, when we talk about discrete systems, you have to explicitly say when they're reacting. So you could say, well, they're all reacting synchronously, according to some clock. You could also say they're reacting at discrete times. Okay? You could say that components react only when an input is present. These are different models. All these models are legitimate models. Yeah.
So if this was a state machine, we could see like one interval or something, the time and state would be. It wouldn't take.
In our model, it's 0 time, okay? And there's a trickiness there, right? Because then at the time of the transition, which state are you in, right? And we're going to come back to that trickiness. And actually, the way we resolve it is we use a super dense notion of time. Instead of saying that the time is the reals, we say that time is modeled by the reals cross natural numbers. So what this means is that instead of saying that, instead of talking about time 1.0, we talk about time 1.00, and then 1.01, and then 1.02, and so on. And the idea here is that at time 1.0, you can have a bunch of events that are causally related, so there's an order to them, but time does not advance between those events. Okay, that's called a super dense model of time. And it's an extremely useful model of time for talking about these mixed, discrete, and continuous systems. Yeah, Ryan.
If you have two guards that are both activated at once in a time system, so I see how that works in a discrete time system, but if you have two guards activated at once,
Right.
that means that the machine exists and moves those states at the same time.
So that's a good question. So if you have two guards out of a state that are both enabled at the same time in a reaction, what does it mean? So in our model, it means the machine is non-determinate, okay? And we interpret that to mean that either of the transitions can be taken, okay? You could interpret it using what is often called a branching time interpretation, which is that your universe forks into two possibilities, okay? So the first interpretation is known as a linear time interpretation. Either is enabled and you take one. The branching time interpretation says your universe forks into two possibilities, and you take both, but now in two different universes. Okay? And the differences between these are extremely subtle. Okay? And they're the subject of a raging debate in the literature that's been going for 15 years at least. All right, but anyway, those subtleties don't worry about. What you do need to know how to do is read these notations. A couple more key points. When we talk about composition of two-state machines, make sure you know what kind of composition we're talking about. So if it's synchronous composition, that means the two will react at the same time instantaneously, okay? Not in some order, okay? And synchronous composition, we have a way of defining exactly what we mean by that, which is to take a composition of two-state machines and translate it into a single-state machine. And this is always the way that we understand the semantics of a composition. We define the semantics of a composition by giving a state machine for the composition. Okay? You should understand how to relate state machines to programs. Okay? You might see some C code on the midterm, and you should understand how to relate it to a state machine. You should be able to read the notation of hierarchical machines. You should be able to know something about the significance of the memory architecture. You should know what interrupts are and how they implement a concurrency model. Okay? And you should have the basic idea that they form the foundation, the implementation level foundation for other models of concurrency on which we build. Okay? And that should, if you got those concepts, you should do fine on the midterm. So I'll see you on Thursday.